Creativity entails a process or product that is recognized as creative by others. Empirical methods with human subjects are often used for external validation, in which one or several judges are involved in evaluating the quality and creativity of the product of a creative task. Let's start by briefly reviewing how these types of external evaluations are applied to judge human creativity. Behavioral tests of creative thinking are common in educational and professional contexts. There is no consensus on the topic, but we will look at some prominent approaches. While this is controversial among cognitive scientists, one of the classic distinctions in cognitive psychology is that between convergent thinking and divergent thinking. Convergent thinking refers to rational problem solving in which a particular solution is expected, and divergent thinking refers to the production of novel ideas through creative thinking and imagination. Tests of creativity in psychology are most often testing divergent thinking, and convergent thinking is tested for measuring analytical intelligence. The Torrance test of creative thinking, or TTCT, is a test of creativity introduced in 1974 that rates the creativity of the subject's response to a variety of tasks on 4 scales. The first rating scale is the fluency scale, which reflects the number of relevant ideas generated by the subject. Then there is the flexibility scale, which reflects the number of categories of relevant responses. This is a sort of measure of the diversity of the responses. Then there is the originality scale. This measures the statistical rarity of a given response. And then there is the elaboration scale. This measures the amount of detail in the response. Other measures and versions of this test have been introduced since the 70s. This test aims to give a general measure of the subject's creativity, so it challenges the subject in a variety of creative tasks, such as the following: an improvement task, which requires listing all the improvements one can think of for a given object; a completion task, repeated 10 times, in which they are given a simple abstract shape to complete; an unusual use task, in which test takers are asked what can they do with a given item aside from its usual purpose, etc. Creativity tests for humans also take the form of personality tests, such as the Epstein Creativity Competence Inventory for Individuals, or EKI. This test, introduced in 2007, uses questions with Likert scale answers to measure 4 types of skills that help people express their creativity. It tests 4 specific abilities: the capacity to preserve new ideas, the willingness to seek challenges, the capacity to broaden knowledge and skills, and the ability to change the physical and social environment. It does not test for creativity directly. Instead, it tests for personality traits that are conducive to being more creative. It has been validated to be a good predictor of creative competency within a sample of more than 13,000 people in 47 countries and has been used on millions of people since its introduction. A version for managers and teachers exists to gauge their skills at stimulating the creativity expression of others. These generic tests designed for humans are quite controversial, and there is a creativity business out there that is often questionable. In our context, the important point is that we cannot apply these tests to machines, although some artificial intelligence systems have been developed to take IQ tests or creativity tests. In general, tests designed for humans are too generic and too tailored to measure human creativity in general rather than the performance at a specific creative task. On the reverse, some tests are too specific. A convergent thinking test that is sometimes used to measure combinatory creativity and associative thinking is the Remote Associates test from 1962, in which participants must find one word that links 3 given words. In a 1996 book, Creativity in Context, creativity researcher Teresa Amabile gives an operational definition of creativity that is also its evaluation method. A product is deemed creative to the extent that observers who are familiar with the relevant domain agree that it is. The novelty here is that the product of a specific creative task is looked at by domain experts. The consensual assessment technique, or CAT, introduced in 1982, consists of a panel of experts who have to judge the creativity of an artwork, a theory, a product, or a performance. It considers the product and not the process, and assumes that in-depth knowledge of the domain is needed, which is why it uses experts. The judges must make their assessments independently, and they not only rate creativity, but also often rate technical quality, aesthetic appeal, originality, and other criteria. If and only if the inter-rater agreement between the judges is high for all the dimensions, we can use the results to draw conclusions about the creativity ratings. The consensual assessment technique has been shown to be reasonably reliable, as outcomes are typically reproducible across sessions. In 2007, Marcus Peer and Geraint Wiggins have used an adapted version of the consensual assessment technique to assess the creativity of a generative music system that composes Lutheran choral melodies given a corpus of existing ones. Again, this is a style imitation task. Instead of asking about creativity, they ask judges to rate how successful is the composition of the choral melody on a 7-point Likert scale. They compared the results for 3 systems with the consensual assessment technique of original melodies from the corpus. The results showed that none of the 3 systems was nearly as successful as the original composers, but that is not the point here. The consensual assessment technique typically focuses on a single creative task, which makes it very appropriate for evaluating creative systems such as those covered in this class. This is the only explicit formal use of consensual assessment technique we know of, but many have used similar Likert scale experiments using expert judges or the general audience to do ratings on various dimensions and to use statistics to discriminate between creative products. Furthermore, as we discussed in our lesson on informal evaluation, we find that jurying, peer reviewing, and curating act similarly. Independent judges are ranking or rating applications as well as giving qualitative feedback. Ideally, this results in a semi-formal evaluation procedure in which only the products which passes the threshold of all the judges get accepted. With the consensual assessment technique, like with other methods, they almost always use indirect wording in the questions in the test. Instead of asking, is a system or product creative, we ask how successful the system was at the task, or we ask about various qualities and defaults of the system. Studies have been conducted that ask how engaging was the system, how boring, enjoyable, simple, complex, organic, mechanical, did it feel, look, or sound. The list of dimensions to be rated seems endless. Computational creativity researcher Graham Ritchie has proposed that the empirical criteria from Margaret Bowden's definition could be used. If so, we would assess Bowden's 3 criteria. We could assess only appropriateness or purposefulness by asking if the product is a solution for the creative task. We could assess novelty, judged in terms of atypicality, given what Graham Ritchie calls the inspiration set, which is the set of creative problems that the system has access to prior to generation. And finally, we can assess the value in terms of quality of the solution. Each of these 3 criteria can be reified independently with subdimensions if deemed necessary. Another common approach to empirical evaluation is to proceed with comparative evaluation between the system's product and human's product for the same creative task. Here, the idea is to compare the quality of a system versus one or more other systems or humans at achieving the same creative task. There are good reasons to proceed with such comparative evaluation. Given the subjective and relative nature of creativity and aesthetic evaluation, it simplifies the evaluation process. Instead of trying to find an absolute measure of the value of the system, like on a Likert scale, which is typically hard, even for a human, comparison grounds the evaluation in a differential. For example, instead of trying to rate the aesthetic quality of a particular product or piece, it might be easier to tell if it is better or worse than another piece, and rank and compare them according to certain dimensions. This comparison can be made across various dimensions and allow us to benchmark systems that are addressing the same creative task. Or we can iterate on the design of a given system and show that the later versions of the systems are actually better than the earlier versions. We saw an example of a synthetic methodology to compare 3 systems with MetaMelo, in the particular case of style imitation, already when we looked at synthetic methods. There are also good reasons to compare a system's product with human products. Humans are the most creative entities we know so far. In other words, humans are the gold standard for creative tasks. So another family of approaches to empirical evaluation is to compare the difference in perception and appreciation between machine-generated artifacts and human-generated ones. Are the system's production comparable to human productions from the corpus or not? Can the audience identify which output are system-generated and which are human-generated ones? Typically, these methodologies use deception. The participants are not told which product is machine-made and which is human-made. These evaluation methods are sometimes called imitation game or discrimination tests. The Turing test is the best-known discrimination test. Designed by Alan Turing in 1950 as a lens to look at the question of machine intelligence, the initial proposal was never meant to be actually carried out. While the Turing test is a test for machine intelligence, one can argue that truly creative systems must have many of the cognitive capabilities of human reasoning and intelligence. The standard Turing test proceeds as such. A human judge gets to interact through text chat with two agents, A and B. If after a fixed period of time, the human cannot tell which of A or B is a computer program, then the test is passed. Occasionally, researchers claim that the test has been passed. We saw an example of one of the latest when we studied the chatbot Eugen Guzman in our lesson on conversational agents. The Loebner Prize is an annual prize that implements the standard Turing test with chatbots. There are various rewards, the highest being for a chatbot fooling the judges while using text, visual, and audio input together. The Loebner Prize will cease if or when that happens. Discriminative tests are controversial because agents that are successful at these tests are only fooling humans for a short period of time, mostly by evading the judge's questions. The Turing test, or one of its many variations, can and has been applied to creative tasks. In this case, one shows some artifacts produced by the machine and some produced by humans, and the participants are asked to guess which is which. A number of alternative tests of intelligence have also been proposed, including question answering in the context of a television show or giving a talk at a TED conference. In a 1843 note, Ada Lovelace wrote that the analytical engine has no pretension to originate anything. It can do whatever we know how to order it to perform. Turing reframed the question to ask whether a machine can ever take us by surprise. In 2001, Brinjog, Bello, and Ferrucci proposed the Lovelace test, in which an intelligent system must originate a creative concept of a work of art. Precisely, an artificial agent A, designed by a human H, passes the Lovelace test if and only if A produced the output O through a process that A can repeat and is not a flug hardware error, and H, or someone with the knowledge and resources of H, cannot explain how A produces O. The test has been criticized for being unbeatable because H, or someone with the same knowledge and resources of H, the human architect, can explain how the system obtained the output. They could even replicate the system, even if they cannot really replicate the result O. It isn't clear that this criticism is founded, but the Lovelace 2.0 test has been proposed by Mark Riddle in 2014 to address this potential shortcoming. The test is really a different one, and it goes as such. Agent A must create an artifact O of type T. O must conform to a set of constraints C, where every constraint Ci that belongs to C is any criterion expressed in natural language that one can think of. A human evaluator H chooses both T, the type of artifact to be produced, and C, the set of constraints that the artifacts must conform to. So this human evaluator H, having chosen T and C, must then be satisfied that O is a valid instance of T and meets C. A human referee determines that the combination of T and C is not unrealistic for an average human. So we need all of those conditions to be the case for the test to be passed. The test has advantages and disadvantages. T and C can be constrained to make the test specific to a given creative task, or they can be left unconstrained to test general creativity and intelligence. The test can be iterated with a single or several evaluators, either the same or different ones, with at least one referee. Statistics can be collected from the various test trends and test configurations. The main disadvantage of the Lovelace 2.0 test seems to be that it does not provide a threshold for deciding that the agent is creative or intelligent. Although, while it tests creative intelligence, it does not necessarily judge talent or aesthetic quality of the output. Here is an example of empirical evaluation of a creative system using human subjects that build on previous work on Turing tests like proposals and discriminatory tests. It was part of a series of studies conducted at the Meta-Creation Lab. We wanted to evaluate the harmonic progression generator we presented earlier in this class. As a reminder, it is a style imitation system that generates chord progressions using a Markovian system based on a corpus of existing chord progressions. We first choose a corpus for this experiment. The corpus we selected is made of 20 excerpts of chord progressions that are each 8 bar long. We selected 2 human-composed progressions and 2 system-generated ones for each of the following 5 classical and romantic music corpuses. There was a corpus by Frédéric Chopin, and here is the list of pieces that were included in the corpus. Then there was Antonin Dvorak, Johannes Brahms, Felix Mendelssohn, and Robert Schumann. The human-composed excerpts were taken directly from the corpus, from the pieces that are listed in bold. We trained the system with the corpus and then generated 2 more compositions with that corpus. There was no curation of the output. The protocol was then that we asked the participants to determine the likely provenance of the source. We did not use deception. The participants knew that some of the compositions were human-composed and some were machine-generated, but they didn't know which was which. We used the 4-point rating scales so they could listen to each of the progressions and decide whether it was definitely human-composed, probably human-composed, probably computer-composed, or definitely computer-composed. This way, we got both a guess for this imitation game and the confidence level. We did not provide a I do not know option. Perceptual studies show that participants tend to underestimate their capability to choose and tend to not know more than they should when these options are available. Let's do the test with you now to give you a sense of the task. Here is one chord progression. Alright, so do you think this is a human-composed chord progression or a computer-generated chord progression? It is not necessarily easy. Here is another one. Can you tell whether it is human-composed or computer-composed? The first harmonic progression is original Chopin, so it is human-composed. The second is computer-generated based on the corpus from Chopin that we selected. That gives you an idea of the task itself in this experiment. The participants came from 2 independent groups. One group had formal training in classical music analysis, which is our target language here, and the other group had no training or just informal musical training. There were 87 participants in total. The musicians had to have 2 years or more of study in a bachelor degree in a music program or to have passed a 5th grade or more at the Royal Conservatory. Out of the non-musicians, just over half of them had some experience and the rest had no experience at all. Statistical analysis of the results showed that the participants were not able to identify computer-composed pieces above chance levels, thus validating our system as being human-competitive in a way. Participants were statistically significantly more confident in their evaluation of the pieces that were human-composed, which was surprising. Expertise did not make a difference. There was no significant difference between musicians and non-musicians that could be observed above chance levels. However, in their comments after each answer, the experts were able to best justify their choice and give much more elaborated explanations, even when they were wrong in their guess. So we can conclude that the chord progression generator is human competitive, but only for a short sequence. Human competitiveness is a concept that we will talk about later on in this course. The algorithm we use here for the style imitation seems to work only between 4 and 32 bars. In longer progressions, there is no sense of beginning and end, and the algorithm fails to articulate and develop more complex forms. These methodologies, based on comparing the products of creative tasks, have limitations. Generative art and computational creativity consist of encoding, at least partially, a creative practice in a process. This creative process can be modeled after an existing practice addressing an existing artistic task like a rule-based system that composes classical music or a painting agent producing impressionist paintings. These systems' products, whether their process is based on the one humans used or not, can still be compared with humans. But there is also a class of systems that use deliberately new processes like using fractals, chaos theory, or multi-agents ecosystems to generate novel and valuable artifacts and experiences. Here, the processes cannot be produced by a human without modern computers. In these cases, it does not make much sense to compare the system's output with a human-made outcome. But one might still want to evaluate the system. Interestingly, it is not always possible for a human to compete in the evaluation when you compare different systems and systems outcomes. Another common criticism of these evaluation methods is that they do not really evaluate the creative process itself, but just the creative outcome. If we evaluate only the product of creativity, not the process, we might get fooled. A very simple approach using templates and randomness can yield very convincing results for someone who does not know how the system works. Reciprocally, a very sophisticated cognitive agent simulations can give a quite poor result that might still be amazing once we know more about the model. Some people talk about weak computational creativity when only the system's product is deemed creative, and strong computational creativity when the process itself is deemed creative. Furthermore, some, like computational creativity researcher Simon Colton, have argued that knowledge of the creative process, that is, an understanding of how the system works, influences the reactions of observers. In fact, this is often true of human-made artifacts. Simon Colton's system, the painting fool for example, which we studied in our lesson on cognitive agents, is capable of justifying its creative choices, and writes a paragraph about each piece made. In conclusion, evaluation methods from generative art and computational creativity raise many challenges. While a lot of work has been done that could not fit into this brief introduction to the topics, there is much more to be done. Several methodological avenues have not been explored yet. For example, movement and physiological data about audience reactions could be used to gauge their emotional and affective response, which might be different from the response reported. Neuroimagery could also be used. These are already used in many perceptual studies. The fields of perceptual modeling and affective computing, which deal with how people express and perceive emotions, have both received considerable attention, and much knowledge transfer is possible. Researchers will keep crafting new research instruments in those directions, I am sure.